Welcome to my video lecture. I am Dr. A.VELMURUGAN, Assistant Professor, Department of Mechanical Engineering, Government College of Engineering, Chettikari, Dharmaburi. In this video lecture from upcoming semester Thermal Engineering 2, Unit 3 Steam Turbine. Previously, we have to discuss about the Module 1 Introduction of the Steam Turbine, Unit 2 Compounding of the Steam Turbine, Unit 3 Impulse Turbine, Unit 4 Reaction Turbine. From Unit 5, we have discussed about the differentiate between impulse turbine and a reaction turbine and throttling governing of the steam turbine. From this slide, we have discussed about the differentiate between impulse turbine and a reaction turbine. Previously, I told about you from impulse turbine and a reaction turbine. From impulse turbine, the steam is completely expanded in the nozzle and its pressure remains constant during its flow through the blade passage. From this impulse turbine, from the blade, the high velocity steam is impinges to rotate the moving blade with the help of high velocity. From that nozzle itself, the steam will be expanded. From that the pressure drop will be happen on the nozzle section, but in that blade section there is no pressure drop in the impulse turbine. But in the reaction turbine, the steam is expanded partially in the nozzle and further expansion takes place in the rotor blade. From the reaction turbine, the steam will be expanded in the 50% in the nozzle section and 50% in the blade section. From the impulse turbine, the relative velocity of the steam passing through over the blade remains constant in the absence of friction. From that impulse turbine, the high velocity steam is impinges to rotate the moving blade. There is no relative velocity. That's why there is an absence of friction. But in the reaction turbine, the relative velocity of the steam is passing through over the blade increases as the steam expanded while passing over the blade. From that relative velocity in the reaction turbine, from the outlet of the reaction turbine is greater than to the inlet blade of the relative velocity VR1. From the impulse turbine, the blades are symmetrical, but in the reaction turbine, the blades are asymmetrical. From the impulse turbine, the manufacturing is very easy, but in the reaction turbine blade it is difficult to manufacturing. But from the impulse turbine, the blade will be profile flow, but in the reaction turbine, the aerofoil flow. The pressure on the both end of the moving blade is same, but in that reaction turbine, the pressure on the both end of the moving blade is different. From that impulse turbine, the pressure drop will be happen on the nozzle section. From the moving blade, there is no pressure drop, but in the reaction turbine, the 50% pressure drop is happen on the reaction turbine and the 50% pressure drop happen on the moving blade. From the same power developed as the pressure drop is more, the number of stages required very less. But in the reaction turbine, for the same power developed as the pressure drop is small, the number of stages are required for more. The blade efficiency curve is less flat in the impulse turbine, but in the reaction turbine, the blade efficiency curve is more flat. Already I told about it, from the impulse turbine is the profile blade, but in the reaction turbine is aerofoil section. From the impulse turbine, the steam velocity is very high. Therefore, the speed of the turbine is high. But in the reaction turbine, the steam velocity is not very high and therefore the speed of the turbine is very low. From this figure, that is we have to show about the impulse turbine versus reaction turbine. From the impulse turbine and the reaction turbine, from this blade we have to rotate the moving blade with the help of high velocity steam impinges on the rotate the blade. From that blade there is axial motion in the direction. The blade will be rotating in the circumferential motion. If the nozzle will be hit to rotate the impinges the blade, means the blade will be rotating on the anti-clockwise direction. From that moving blade section, there is a two section. One is a nozzle section, another one is a moving blade section. From the nozzle section, there is a pressure drop in the nozzle section, but in the moving blade there is no pressure drop. The pressure will be remains constant, but in the velocity simultaneously from the nozzle section, the velocity will be increasing from that nozzle section. After, from the moving blade, the velocity will be decreasing in the moving blade in the nozzle section. Then from that low velocity in the moving blade section in the impulse turbine. But in the reaction turbine, the flow, the steam will be rotating, and the rotating will be smoothly in the nozzle. Here the blade is acting on the nozzle view, and also the high pressure steam is entered to the reaction turbine. Sorry, high velocity steam is entered to the reaction turbine. From here the pressure drop is happen on the nozzle section. After from the it goes to the steam is goes to the moving blade, again the pressure drop will be happen on the moving blade section. But in the velocity from the nozzle section, the high velocity will be happen. The steam is enters to the moving blade, the velocity will be decreasing. From this impulse turbine and reaction turbine, the very important points are, from that impulse turbine the pressure is constant in the moving blade. Pressure is constant in the moving blade. There is no any changes in the moving blade. But in the reaction turbine, the pressure will be changing. From that it goes, the steam will be flowing from the nozzle section and also moving blade section. There is a pressure changes will be happen on that reaction turbine. From that second point, the enthalpy is constant in the moving blade, but in that reaction turbine, the 50% of the 50% enthalpy drop in the nozzle section and 50% enthalpy drop in the blade section. The enthalpy is not constant; it is decreases in the moving blade. From the impulse, already I told about it. From the impulse turbine, the relative velocity is constant in the moving blade from impulse turbine, but in the relative velocity is not constant in the moving blade from that reaction turbine. From the impulse turbine, the relative velocity inlet angle and equal to outlet angle. The relative velocity inlet angle equal to outlet angle. But in the reaction turbine, the outlet relative velocity is greater than to the inlet relative velocity. Next slide, very important. We have to control the speed of the turbine with the help of the governing of the turbine. The governing is the method of maintaining the speed of the turbine constant irrespective of variation of the load on the turbine. The main objective of this turbine is to rotate the governor, increase and decrease the load to maintain the speed of the turbine. The types of governing is method to use in the steam turbine to maintain the constant speed of the governing of the turbine. The main function of this, main objective of this governing of the turbine is to maintain the constant speed of the governing of the turbine. From these various types of governors are present to control the speed of the blade in the turbine. A governor is used for achieving this purpose, which regulates the supply of the steam to the turbine in such a way that the speed of the turbine is maintained as far as possible, a constant under varying load condition. The various method of governing of the steam turbines are: first one is throttle governing, second one is nozzle governing, third one is bypass governing, fourth one is combination of throttle governing and bypass governing, fifth one is combination of nozzle governing and bypass governing. First slide we have discussed about the throttle governing. The throttle governing is the quantity of steam is entering into the turbine is reduced the throttling of the steam. The throttling is activated with the help of this double heat balanced valves, which is operated by centrifugal governor. Through this servo mechanism, the effort of the governor is not sufficient to move the valve against the piston with big units. The small operated relay from the servo mechanism is incorporated in the circuit to magnifying the small force to produce the governor to operate the valve. Throttle governing, that is a centrifugal governor attached with the fly ball and spring adjustment, the sleeve mechanism. After that, a differential lever is attached from coupled with the governor, that is a fulcrum lever, and also the hand wheel adjustment for initial adjustment for the throttle governor. After that, there is a two types of cylinder. One is a positive pilot piston, another one is a relay piston. From here the oil cylinder and servo motor cylinder, hand wheel adjustment and initial adjustment, the passage of oil will be returned from this passage. Finally, that is a throttle valve. Here the path of the steam is from inlet condition to outlet condition, and the oil pump and the bevel gear. The turbine shaft is connected from the output of the turbine shaft. From the position of the governor sleeve, The positive pilot piston is, these are all the very important components from this throttle governing. One is a position of the governor sleeve, positive pilot piston and relay piston, full load turbine and energy supplied steam in the same. From this condition, the throttle governing from this governor, that is a from that this diagram is mainly denoted for the full load condition, for that turbine is operating from the full load condition. If we happen any other decreasing the load, we have to reduce the load from the steam is, we have to control the steam in from that steam is goes to the steam out from the turbine conditions, we have to control the speed of the turbine. But in that outlet condition is very same, but the mass flow of the steam is same, we have to control the steam with the help of this throttle valve. The main function of this throttle valve governing is the simple in operation, the thermodynamically inefficient of the available of the heat trap is reduced irreversible throttle process. This process is called a throttle governing process. So initially the governor will be attached with the help of the fly ball. The fly ball, the sleeve will be moving from this direction. After that, with the help of this link mechanism, that differential gear mechanism, the pilot piston is acting on the upward direction, but in that piston, the relay piston is acting on the downward direction. From this downward direction, to reduce the decreasing the load in the turbine, they should lock the sleeve. This is irreversible process to output of this turbine. This process is called a throttle governing process. Next slide, we have discussed about the graphical representation of Williams line from the y-axis steam consumption, from x-axis load. From this linear line is present from this Williams line. If the efficiency is increasing, means the fuel consumption will be simultaneously proportional to, that is proportional from the efficiency. For efficiency will be increasing, means automatically the steam consumption will be reduced. From here K is a constant. This line is a Williams line. Next slide, we have discussed about the another one of the throttle governing. The governing is a nozzle governing. From we have to control the speed of the turbine with the help of this nozzle. Here there is a three valves adjustment: valve 1, valve 2, valve 3, and also there is a pipeline, connecting pipeline. From valve 1 is connected to the nozzle 1, from valve 2 pipeline is connected to nozzle 2, from valve 3 pipeline is connected to the valve 3. From that, if we have this operating condition is from that full load condition, the turbine will be reduced. If the steam flow will be controlled or the decreasing in the load conditions, we have to, the valve will be closed from this condition, from the valve will be closed. If you have valve 1 is closed, means they have automatically to the nozzle flow will be reduced. Nozzle high velocity steam will be controlled with the help of this nozzle. If the valve will be blocked, means the flow, it is this valve is not hinged to rotate the turbine blade. This is a nozzle governing turbine. Next governing turbine is a bypass governing. When this turbine is overload condition for short duration, during such operation is bypass valves are opened and fresh steam is introduced into the later stages of the turbine. This generate more energy to sacrifice the increase the load. From this bypass governing, we have to control this throttle valve with the help of that inlet steam goes to the outlet conditions. We have to, from the initial condition, the load will be short duration, so that condition the steam is leaving from the bypass circuit. These losses in the steam turbines are, main losses are residual velocity losses, losses in the regulating valves, losses due to steam friction in the nozzle, losses due to leakages, losses due to mechanical friction, losses due to wetness of the steam, and finally it is a radiation losses. These are all the losses happen on the turbine. Next slide, we have discussed about the effect of blade friction in the steam turbine. From the enthalpy entropy diagram, this line is showing from the saturation line. From here, pressure P1, P2, P3, P4, P5. So depending upon that normal condition, from that ideal condition, the process will be happen in the isentropic expansion in the turbine process 1 to 2. But in the actual condition, it will be goes on the above the saturation line from the superheated steam. The overall efficiency and reheat factor. The reheat factor is defined as the ratio of the cumulative heat trap, adiabatic heat trap in all the stages of the turbine. The valve of reheat factor depending on the type and the efficiency of the turbine. the average blade being the 1.05. If you find out the reheat factor, means that is a cumulative heat drop or adiabatic heat drop. And also we should find out the overall efficiency of the turbine, means it is defined as the ratio of total useful heat drop to the total heat supplied. The overall efficiency is total useful heat drop by total heat supplied. Thank you.